Okay, first thing we're going to be talking about today is what's called average atomic mass and how it's calculated. So one term that we brushed on the other day, I don't know if we made it 100% clear, but in nature there are things called isotopes. All right, we mentioned that every atom has a set number of protons and that can never change. Otherwise it becomes a different atom entirely, a different element. All right, what can change is the number of neutrons that are in the nucleus. All right, you can have two carbon atoms that have different numbers of neutrons, but they're both still carbon. And those elements that have different numbers of neutrons are called isotopes. All right, and the effect of having a different number of neutrons is that those two atoms are going to have different atomic masses. So when you're trying to specify which atomic mass or which type of isotope you're talking about when you're writing about chemistry, you'll write the atomic symbol, which is just the letters that are on the periodic table, followed by a dash, and then the atomic mass of the isotope you're talking about. So carbon with an atomic mass of 14, you would write as C-14. All right. Okay, so atomic mass in general is the total number of protons and neutrons in an atom. So each proton or neutron counts for one atomic mass unit, or AMU. But when you look at the periodic table, all of the masses that they give you are decimal numbers. So like nitrogen here, it's rounded, or it's written out as 14.007. Where is that 0.007 coming from? Now, the easy answer would be, it's the electrons, right? If the protons and neutrons count for 1 each and they add up to 14, all the electrons flying around out there must add up to the 0.007. And that's not right, right? It'd be convenient if it was, but that's not true at all. Those electrons are so tiny compared to the protons and neutrons that they have effectively no impact on the mass at all. They don't matter. So this 0.007 has to be coming from something else. All right, and the way that they get those decimal masses for all of, like the one here on the nitrogen, is by basically averaging together all of the different isotopes, the different types of the element that are out there, into one average mass. All right, and it would be easy if you could just say, all right, we have copper 12 and copper 14, add them together, divide by 2, that's an average, the atomic mass must be 13. The problem is all those different isotopes don't occur in the same abundance out in nature, right? In nature, carbon 12 is way more common than any of the other isotopes. So it should make sense that that has more of an impact on what the average atomic mass should be if it's the one that is the most common. So the way they do that is by using a weighted average. All right, so there's 3 steps to calculating the weighted average of an element and its isotopes. So for all these problems, you're going to be given the isotopes and you're going to be given the abundance. So here, if it's carbon 12, we know it has a total mass of 12, 6 protons and 6 neutrons. And the percentage in nature, or the abundance, how much of it there is relative to the other isotopes, in this case is 98.89%. So pretty much all of it is carbon 12. Carbon 13, you can see 1.11%, and then carbon 14 is the rarest at, less than 0.01%. So what we're going to do in order to calculate this weighted average is, first off, we're going to convert all of these percentages to decimals. So to do that, we divide by 100, or you move the decimal place to the left. It does the same thing. So here, the 98.89. Of course, I get a pen that doesn't work. 1 second. Okay. So the 98.89% divided by 100 is equal to 0.9889. So if you don't believe me, you can plug it in your calculator. .9889 divided by 100. 0.9889, and you can see how that's just taking this decimal place and moving it to the left, just like we were doing when we were doing scientific notation. All right, so 0.9889 is for the carbon 12. For the carbon 13, if we move that decimal point to the left or divide by 100, we're going to get 0.0111. And then the carbon 14, I mean, that one's going to be 0.0001, right? Or even less than that because it has the less than sign, but we'll leave it at that for now. All right, so that's step 1. Step 2, we're going to take the mass of each isotope. So that's the number that comes after the name there. Carbon 12, carbon 13, carbon 14. And we're going to multiply that by the decimal of its abundance. So this 9889, we're going to multiply by 12 because it goes with the carbon 12. The 13, we're going to multiply by the 0.0111. And then this one, we're going to multiply by 14. All right, so this first one, 0.9889 times 12. So we can say times 12. Comes out as 11.8668. The 0.0111 times 13 is 0.1443. So 0.1443. And then our 0.0001 times 14 is equal to 0.0014. All right, and then your last step is to take these three numbers you got by multiplying those and add them all together to get your final answer. And that final answer will be the average atomic mass of your element. So 8 plus 3 plus 4 is 15. Carry the 1 over. That's 7 plus 4 is 11 plus 1 is 12. 6 plus 4 is 1 or 10 plus 1 is 11. And that one's a 0. And then we get that. So 12.0125 would be our average atomic mass of carbon if these were the relative abundances. All right, so it's really not that complicated. It's just a couple of steps you got to remember, and you got to practice a little bit. All right, so we'll do 2 more practice problems together, and then I'll set you guys loose to work on the homework. All right, so this one here says that the element copper has naturally occurring isotopes with mass numbers of 63 and 65. The relative abundance and atomic masses are 69.2% for copper 63 and 30.8% for copper 65. And it wants us to find the average atomic mass of copper. So first step, if we go back a slide, is to convert the percentages of the abundances to decimals. So this 69.2, if we move the decimal place 2 over, divide by 100, we get 0.692. And then the 30.8, we're going to do the same thing and get 0.308. All right. Step 2 is to take those percentages and multiply them by the mass of the isotope that they go with. So the 69.2, or our 0.692, we're going to multiply by 63, because that's the isotope it goes with. So times 63. And this 0.308, we're going to multiply by 65. All right, we'll plug those into the calculator and see what they come out as. 0.692 times 63. That's 43.596. And then the 30.8, or sorry, 0.308 times 65 is equal to 20.02. So when we add these together, so we'll just say plus our 43.596, we get 63.616 as our average atomic mass. Okay, pretty straightforward. We'll do one more together. All right, the average atomic mass of bromine is what it wants to know. And it tells us that one isotope of bromine has an atomic mass of 79 and an abundance of 50.69. And the other major isotope has a mass of 81 and an abundance of 49.31. So again, the first step, convert those percentages into decimals. So 50.69 is going to end up as 0.5069. And the 49.31 is going to end up as 0.4931. Again, all we're doing there is moving that decimal point 2 to the left. Okay, then we're going to multiply each one by the mass that they go with. So the 50.69 is the abundance for the isotope that has a mass of 79. So we'll say that times 79. And then the 49.31 is the abundance for the mass of the isotope that is 81. So you multiply that by 81. Plug that into your calculator. 0.5069 times 79 is 40.0451. And then we've got 0.4931 times 81, the mass of the isotope there. And that's 39.9411. All right, then to get our total final atomic or average atomic mass, we just add those two together. So that plus our 40.0451 gives us an average atomic mass of 79.9862. All right, so you guys have got a homework assignment that's got a bunch of problems like this. I want you to go through, do as many of them as you can today, and just get some practice, because this is something that if you don't practice on, it's easy to slip up somewhere in the process and make mistakes and, you know, lose points on a test or whatever. So I'll let y'all get to work on that.